Do you hear it? You can start now.
Yeah.
Good.
So I will start. Okay, good afternoon, everyone. I'm happy to present our work. The title is "Are we really achieving better beyond accuracy performance in next basket recommendation?" This work is cooperated with Ming, Sami, Jullien, Mozhdeh, Ariannezhad, Mohammad, Aliannejadi, and Maarten Rijke. I will introduce our work from four aspects: the motivation, purpose, the method, experiments, and the results conclusion. Next, basket recommendation, for short MBR, aims to model users' preference based on a sequence of historical baskets, and the model will predict for each user a set of items they are likely to buy next. In the predicted basket, there are two kinds of item. The first kind is a repeat item, means the item that the user has bought before. For example, this milk, the user has bought it in the previous basket, so it's a repeat item. And another kind of item is explore item, means a new item to the user that the user never bought it before. So I will introduce the motivation of our work. In the MBR task, the repeat items and the explore items, they appear in the predicted basket at the same time. And from a paper, a next basket recommendation reality check, they find that most of accuracy comes from the repeat items prediction. To give you an intuitive feeling, here is a plot tested on the Dahomey dataset. The x-axis is different MBR method, the y-axis is recall. And the blue bar represents the accuracy comes from the repeat item, and the orange bar is the accuracy from the explore item. So it's obvious that the accuracy from repeat items is far more than the explore items. And also in the MBR task, the beyond accuracy metrics remains largely unexplored. So we propose a potential shortcut in MBR setting. This shortcut is we predict the repeat items to achieve a very good accuracy, and we use the explore items only optimized for beyond accuracy metrics. For example, item fairness and diversity. When we combine these two parts to generate the final basket, we hope the final basket can have a good accuracy and beyond accuracy at the same time. And in this table, I list all the beyond accuracy metrics invested in our work. There are 5 fairness metrics, item fairness metric, and 3 diversity metric. First, let's start it from item fairness metric. It's about assigning exposure to the items based on a fairness principle. The first kind of principle is equal opportunity. It means the exposure should be assigned to the items based on their relevance. If this group of items have more relevance, then we give them more exposure. So we choose log EUR, log RE, log EUR, log RUR, and EL. And the second category is statistical parity. It's different group of items, they should have equal average exposure result considering the relevance. We choose EED, log DP metric, and also 3 well-known diversity metric, ILD, entropy, and DS. And also we classified all of these beyond accuracy metrics into 3 level of accuracy connection. This is obtained from the definition of each metric. To what extent is relevance considered when calculating this metric? So there are 3 accuracy connection levels: strong connection, weak connection, and non-connection. And then I will introduce our proposed method, a 2-step reputation exploration framework, TREX. This framework consists of 3 modules. The first is the exploration module. This module will generate a explore items list for each user. And we have 2 variants. One is designed for optimizing item fairness, called EX Fair, and one is designed for optimizing diversity, called EX Diversity. And then in the repetition module, this module will learn the user's history interaction and predict the repeat items list for the user. And in the final basket generation model, we will combine these two parts to generate the final basket. So the whole framework also have two variants, the TIEX step and TIEX diversity. Their main difference is that they use different exploration module. Then let's go to the detail of each model. For the repetition module, we design a simple but effective method. This module consists of two parts. The first part is personal purchase frequency with time decay. Here we use a time decay factor to give the recent interaction more impact on the score. And the second part is item-specific repurchase feature. I can give you an example. It's like people buy the milk maybe once a week, so it has a high repurchase score. And for the pot, maybe people buy it once a year. So milk has a higher repurchase score. And when we combine these two parts, we get the repetition score for the user to the item I. And for the exploration module, the first variant is designed for item fairness. Here we study the item fairness between popular item group and unpopular item group. Our strategy is we randomly sample the unpopular items based on a probability to generate the explore item list. And for the X diversity, we use the items category to compute the diversity. Our strategy is we add items with a new category iteratively. So for each new added item, it has different category with the items already in the basket. Then in the final module, basket generation module, we have a fixed set of basket with like 10 or 20. First, we prioritize repeat items. We use a threshold way to filter the repeat items list. Only when the repeat score is larger than we, then we will fill them into the basket. And then if there are some remaining slots, we will fill them with explore items. So our framework is very flexible because we can adjust the way to control the proportion of repeat items and explore items in the basket. And in the experiment setup part, we use two grocery shopping data sets, Instacart and Homebee. Their main difference is they have a different repeat ratio, means the average proportion of repeat items in the ground truth basket. For example, Instacart, the repeat ratio is 0.6, and the explore ratio is 1 minus repeat ratio. And for the NBR baselines used in our work, we use 3 simple frequency-based methods and 2 nearest neighbor-based methods, TIFKN, UPCF, and 3 neural network-based methods. Here, the dream is based on the RN and the DNTSP is based on graph neural network. RecNet is a repeat consumption-aware neural network. For the accuracy metrics, we use recall and DCG PHR, personal hit ratio in our work. Here, the recall is the main accuracy metric in the experiment. For the beyond accuracy metric, I have introduced you in the table. There are 5 item fairness metric and 3 diversity metric. And let's see the experiment and results part. The first research question is, what's the accuracy performance of repetition module? In this experiment, we evaluate accuracy of repetition module with other NBR baselines. And the conclusion is that first, the repetition module always achieves or matches the state-of-the-art accuracy on both datasets across different accuracy metrics. And also, we found that compared with 2 deep learning-based methods, DREAM and DNTSP, our repetition module also surpasses them in terms of accuracy. So here we show that the complex deep learning model, sometimes they have worse performance than a very simple recommendation module. And the second research question is, what's the accuracy diversity trade-off? What's the accuracy diversity performance of TREX diversity? In this experiment, we evaluate the recall and three different diversity metrics of TREX and other baseline. So here I give you a representative results. In this plot, the x-axis is diversity metric ILD, and the y-axis is recall. A method should have larger ILD and larger recall. So I use a red cross to show the error with better performance. And this is a line of green triangle that is the TREX diversity because we can adjust the threshold in the basket generation model, so we can control the value of V to get a accuracy diversity trade-off about the TREX diversity. And this blue area covers many baseline NBR baseline. Each node represents a NBR method, and we can see that TREX shows the best accuracy diversity evaluation compared with other baselines. And also on the another two diversity metrics, it shows the same pattern. Then the third research question: what's the accuracy fairness performance of TREX fair? In this experiment, we evaluate the accuracy and atom fairness metrics of TREX fair and other baselines. And here I list two representative patterns. Let's first see the first one. The x-axis is the log UR fairness metric. The y-axis is recall. I also use the red cross to show the error with better performance. And this is a line of orange triangle is the TREX fair. It also we control the threshold way to show the trade-off of TREX fair. And the others node, each node represents a baseline. We can see that in this plot, our TREX fair is better than other baseline. However, in the second plot, the x-axis is log RUR, that is another fairness metric. In this plot, the TREX fair is not always better than other baseline. So in this table, we count all the beyond accuracy metrics and their shortcut success rate. Means on the two data set, on how much data set we successfully use the TREX to get a better accuracy and beyond accuracy performance. And we find that this success rate has a relation with the accuracy connection. So the log UR has a strong accuracy connection. The success rate is 0. But for the weak connection, sum is 2, sum is 1. For the non-connection, we success on all the data set, two data set. So we get a conclusion is it's more difficult to leverage this shortcut to beyond the accuracy metrics with stronger accuracy connection. Then we will ask a question: does TREX really achieve a better accuracy and beyond accuracy performance? Because based on the previous experiment, the answer seems to be yes. But when we go deeper to do some fine-grained level analysis, like the research question 4, what's the exploration accuracy of TREX? In this experiment, we only evaluate the accuracy of explore atoms obtained by the TREX diversity and the other baselines on the two data set. So it's clear that the TREX diversity has much lower exploration accuracy than other baseline. So this is within our expectation because our TREX framework, the exploration model, doesn't consider the accuracy. But we think it's unreasonable to sacrifice the exploration accuracy of TREX, expecting it's being low. Because some users, they like to explore new atoms. It can be reflected by the statistic of the dataset. You can see the explore ratio 0.4, 0.57, so it's quite high. And also, we use the TREX framework to identify the shortcut. But this shortcut also reveals that there is a potential flaws of the existing evaluation paradigms in next basket recognition. I mean, the overall evaluation evaluates the whole basket. So we propose that a fine-grained level evaluation is needed to give us a more comprehensive understanding of the NBR method, like a separate evaluation, like what we did in research question 4, evaluate the explore atoms and repeat atoms separately. So to conclude, in this paper we propose TREX to identify the shortcut strategy in achieving better accuracy and beyond accuracy performance in next basket recommendation. And we end up challenging the traditional overall evaluation paradigm and think that a fine-grained level evaluation is necessary to give a comprehensive and detailed evaluation of all the NBR methods. So that's all the content of our work. Thanks for your listening. Do you have any questions?
Okay, thank you.